do is the integral over this closed curve of f evaluated at r of t dotted with r prime of t dt, right? And I would have a lot of work ahead of me because I've got to find the parametric representation of c. Could I do that? How could you draw out c here? This is r of t, right? We need to draw this circle, radius 3, so 3, vector, 3 cosine t, 3 sine t. Then I would have to take the derivative of this and replace every x in here, right? To do this part, I'd replace every y with sine t, every x with 3 cosine t, and then dot that with the derivative of this, and then, oh my God, do we want to write that down? Do you want to see what that looks like? I don't. But do you appreciate how nasty that is? Yes? Okay, so instead of this, let's look at the region D. Ah, nice little circle. That's a nice region, right? We like that. That's a polar region. We can define that very nice. So let's convert this over to a double integral using Green's theorem. So what would we have here? This becomes the double integral over the region D of the partial of q with respect to x. Now that looks like it might be bad, but let's see if it is. What is the partial of q with respect to x? 7 minus the partial of p with respect to y. 3 dA, which is 4 double integral 1 over d of 1 dA, which is the area of our region, which is pi r squared, which would be 9 pi, which is 36 pi. Done. While some poor soul who's never seen Green's theorem is sitting there plugging in, and just imagine just what this first part would look like. You know, just that part. If I plugged in for x, I would be trying to integrate e to the sine of 3 cosine of t. I mean, and that's not even dotted out with the other parts yet, you know? That's nice, huh? I mean, that's what you can do to your friends who don't know Green's theorem, you know? You can do something really like nasty. You could give them like, and just think about how easy this would be to make a really hard problem. You could be like, okay, do like 2y plus x to the natural log of cosine, x to the natural log cosine of y squared plus 1, right? Something like that. Dx plus, and then just this next one, just give it a nice little x component, like x part, so that give it like, you know, x, and then the rest of it a bunch of crap with y's in it, right? And then give them some circle and tell them to do the line integral, and without Green's theorem, it's a disaster, right? Probably impossible to do.
Did that happen to your brother once? He said like something about a class where like...
It was a little different. It wasn't a problem like that, but... Okay, so in this I asked to do it by line integrals and then by Green's theorem. And then when we do it by line integrals, I actually said, see, we don't want to do this, right? And we don't... So this, I never actually do this in class. Don't think I do, all right? All right, so we can see that sometimes computing line integrals over a closed curve is easier when we use the Green's theorem, right? And convert the problem to a double integral. There are other cases when we can convert a double integral into a line integral. Now, this is a little different though, okay? It's a little bit, there's a little subtle difference here we have to be careful with. So let's think about something. Remember, you all know this now, obviously, that the area of a region D is going to be given by this double integral. So coming back here, right, and looking at the Green's theorem, the only way that we would be talking about the area of D is if this was a 1, right? And the only way that that can be 1 is how? Like, how are some ways that that could be 1? So here's one way. What if P was 0 and Q was X? So remember we had our vector field was PQ, right? Which we were writing like this, P dx plus, it's right up here to my right, but putting it on camera. So how could this situation be converted to, when it's converted to the Green's theorem, how could we make it that this is a 1? So we could make it so that if the Q was X and the P was 0, so if this was X and this was 0, then when you did this partial, wouldn't you get a 1? Yes. Okay? You could also have that P is negative Y and Q is 0. So if this is negative Y and this is 0, then when you do the partial of this with respect to X, you get 0. And we do the partial of negative Y with respect to Y, you get negative 1, and you put it right here, and you have minus minus 1. It's going to give you 1. Right? So that's two ways you could do it. And then you could do it this way also. You could let P be negative 1/2 Y and Q be 1/2 X. And if you took the partials, you would get a 1 here. So I'm just showing you there are various ways that you could define your field in order to get a 1 in here. So who cares, right? Like, why is that important? Let me show you. Find the area of a circle with radius r. Okay, I did this in Cal 2 I did it, and then with my students. And then I've done it this semester, and we used polar coordinates. Do you remember that? We proved it with polar coordinates. It was pretty quick, too. It was pretty fast. But I want to use Green's theorem to do it. All right? So here's where we are. We are trying to find the area of a circle with radius r. Okay? Well, we could just do a double integral, couldn't we? We could just do a double integral? Yeah? But instead of doing that, what I'm going to do is I'm going to use this backwards. Okay? So I want the double integral over d, here's d, of 1 dA, right? That's what I want. That would give me the area of d. But I'm going to turn that into the double integral over d of partial of q with respect to x minus partial of p with respect to y dA, where q equals x and p equals 0. So I'm telling you, look, that one, I'm rewriting it as these two partials subtracted, where I'm defining the q and the p to be these two. Why do I define them this way? Because when I take the partial of this with respect to x, right, I get 1, and when I take the partial of this with respect to y, I get 0. So that q and that p would work, right? So now I'm here. Now go back up to this. So that would be, this now turns into the line integral over c, right, of p, which was 0 dx, plus q, which was x dy, right? Okay. Y'all okay with this? Now, pay attention. Now we are talking about the curve C as opposed to the area, the region inside, right? We have transformed this double integral over D into a line integral. Yes? All right. Now, I will admit that this is a longer way to get the area, but I think you'll really appreciate this in the next example. All right, so I need to do this integral right here. This is gone, isn't it? That's 0, gone? Okay, so really, this at the end of the day becomes the line integral over c of x dy. And this is your good old line integral with respect to y. Like, this is not a vector line integral. This is your scalar line integrals. This is the curtain problems. Remember those? So all I need to do is find a parametric representation of the curve C. So how could you give me that curve C? How could you do the parametric representation of it? Okay, so R of t is, this is C, right? C is equal to R of t, which is the vector. We've done this. Oh, wait, it's not cosine, it's R cosine t and R sine t, because it's an arbitrary radius. Okay, so this is your x and this is your y. So let's just plug that in here. What were our limits on t if we're going to draw that curve? Sorry, I didn't put that here. 0 to pi. Okay, so this line integral becomes integral 0 to pi, and then I have x, which is R cosine t, times dy, which is the derivative of the y component, which is derivative of that, R cosine t again, dt. Now r is a constant, so it can come out, r squared integral 0 to pi cosine squared t dt. And how would you integrate cosine squared? Power reducing formula? So that would become r squared integral 0 to pi. And then the 1/2 would come out, wouldn't it? I'm going to pull out the 1/2 here. 1/2. Then I'd be integrating 1 plus cosine 2t, right? Almost done. Let's go ahead and integrate. So 1/2 r squared, antiderivative of 1 is t, antiderivative of cosine 2t is 1/2 sine 2t, evaluating 0 to pi. So what do you get when you plug in 2 pi? 2 pi plus 4 pi, sine of 4 pi is 0, so you just get 1/2 r squared times 2 pi, yes? 1/2 r squared times 2 pi, then minus what? 0. So the 2's cancel and you get pi r squared. That is the longer way to show that the area of a circle of radius r is pi r squared. But now you've seen it 3 different ways, right? That's kind of cool. Any questions here? Yes? If what is 0? Well, that's... I'm not quite sure I understand the question. Because this is the formula, isn't it? Right? The formula is that to check whether or not a vector field is conservative, you see if the partial p with respect to y is equal to the partial q with respect to x. If they're equal, then this would be 0, right? I think that's what you're getting at. If this is 0, then this would be a conservative vector field. But I'm not quite sure how you're relating it to this.
That comes from here.
Yes. Like, does that check come from here? Yes. In the proof of the theorem, it does incorporate this part, yes. In the proof of Green's theorem, are you talking about in the proof of Green's theorem? Yes, we use that. I don't even know if the book sketches the proof for Green's theorem or not. I'll have to check. I don't know if it does. Okay, let's move on. So really, when it comes down to it, if somebody gives us a 2-dimensional region, we might be able to come up with its area using a line integral, as opposed to a double integral. In this case, I don't think it would have been worth it. I would have stuck with a double integral on this problem, wouldn't you? That would have just been, what would this double integral? We've already talked about it. This would be 0 to r, 0 to 2 pi, 0 to r, and then it would be r dr d theta. And that's all it would have been, and we would have been done a long time ago. But something like this, a little more complicated. What's the area of this region enclosed by this curve? Strange, huh? Strange shape? So what we're going to give you here is the actual parametric equations that draw this thing. There they are. You have the x and the y. So this is really, if you put this in a vector like this is like your r of t right here equals this, comma, forget the y, right? Do y'all see that? That's like your vector function that draws that weird curve. Find the area of that. Understand? So how would you do this with the double integral? What type of region is that? It's not even a polar region, okay? It's not. It's something else. It's just crazy looking, right? I don't think you're going to have success with the double integral here. I don't think you will. So instead, let's use Green's theorem. For Green's theorem, to find the area of this, we're going to say, look, this in here is D, right? The curve going around it, all the way around, back around, that's C. Yes? And so the area is the double integral over d of 1 dA, but that should be equal to the line integral over the closed curve C of partial, so I'm using this right here, q with respect to x, minus partial p with respect to y, d, what am I doing here? D, wait a minute, d, what the hell am I doing? I don't know why I did that, not ready to go to a line integral yet. Double integral over d, dA. So I'm rewriting this one. What are we going to use for p and q? We can choose it. There were 3 different examples I gave you. You want to stick with q as x and p as 0? Why not? Why not? Okay, let's go with q as x, p as 0. If I do that, then what does this double integral become? Line integral over c of what? 0 dx plus x dy, right? So it's the same integral we did before. The only difference is what's x for us this time? Well, that's this, right? That's x. And then what's dy? It's the derivative of this. We have to take this y and take its derivative, right? And multiply them together and do our integral. Where would the integral go from? What would our restrictions on t be? 0 to 2 pi. So let's set it up. I don't think I'm going to do it, but let's set it up. This would become the integral from 0 to 2 pi of x, which is 5 cosine t minus cosine 5t, times the derivative of this with respect to y, which would be 5 cosine t minus 5 cosine 5t dt. Then you'd have to FOIL things out, right? So y'all understand that this is dy and this is x. Okay, just out of curiosity, would this been any better had we used one of the other 2 formulas that I gave you? So would it have been better? I said one way we could achieve this is by letting q be x and p being 0. We could have also achieved this with p being negative y and q being 0. P being negative y and q being 0.
Wouldn't you just give them the same thing?
What would happen if p was negative y and q was 0? So this would have been line integral over c of what? Negative y dx. And then this part would be gone, right? Now, is this any easier?
No.
You're doing negative y, which is this, and then you're doing dx, which is that. Still not that efficient, right? Yes? Were you say something? No? What was the third option? Let me go back to it, show it again. The third option was p was negative 1/2 y and q was 1/2 x. P was negative 1/2 y and q was 1/2 x. So what would this become up here? We would have line integral over c, and then we would have p, which is negative 1/2 y dx, plus q, which would be 1/2 x dy. Does that look any better? No. So there's like 3 different options there. They all are going to require that we are going to have to do some expansion here and do some integration. But I just want to be clear, the book provides you with 3 different options. All right, now I actually had the computer do this for me. So I had it expand out this thing and do the integral. And I also did it by hand myself. And the only thing that becomes a little bit tedious on it is that you have to use, there's one part, let me show you where it is. Before you do the integration, when you expand that, and you have to do this integral right here, when you expand it, you'll have a cosine squared t, which you'll use a power reduce. You'll have another cosine squared t out here, but it's cosine squared 5t, so you'll do a power reduce there. The only trouble part was this piece right here, because it was cosine t, cosine 5t. And you go back to pre-cal and you use your product to sum formulas for your trig functions. So if you have a product between 2 trigs, you can turn it into a sum. And once you turn into the sum, then you can do them piece by piece. Other than that, it's pretty straightforward. I think, yeah, 30 pi is the final answer. See here what I'm doing. Okay, let's let this. Just read it real quick. Okay, we're going to make this an in-class group quiz. You can work with up to 4 people in a group. Turned in today. Everyone does their own piece of paper. Yes? You have until the end of class. Pop quiz, what? I thought I was in Cal 3 today. What happened? You can work together. Okay, that's it though. You can't see it anymore. I'm just kidding. Hold on. I'm going to make it a little bigger so you can see it. Maybe not. That's good. While that's happening, I'm going to hand out your next